All right, so I've got your homework number 5, and homework number 6 will be due a week from today. And a week from today, we have our first exam. In class on Thursday, next time we meet, we're going to spend a little bit more time talking about pumps, which is the subject of today's lecture. And I'm also going to give you the design project for the semester. So I'm going to assign that, and it's having to do with a closed conduit network, a pipe network. And today and Thursday will be the last lectures we have on closed conduit flow. And after the exam, we're going to be starting on open channel. The rest of the semester will be spent on it. So any questions on the announcements? It is, yeah. And homework 6, actually, I think that you can solve all of those problems after today's lecture. The lecture we're going to have on Thursday is about affinity laws, which is a way of combining pumps together. And I don't think that one of those problems is on affinity laws. I think that if you'd like to solve homework 6 early, then you can check that with me and feel comfortable with it before we have the exam. For the exam, you'll be allowed to use the equation packet that I've provided before, and one equation sheet beyond that, something of your own preparation. One sheet front and back. Anything you want. Anything you want. It can be equations, it can be column heading titles, so that gives you an idea of how to do certain numerical procedures, supportive notes from family members, pictures of dollar bills to remind you why you're here, anything you want on that equation sheet / resource. It's probable. I haven't written the exam yet, so I can't promise it to you, but it's probable, yeah.
And we can't use prepared spreadsheets?
No, you can't. You wouldn't want to. You want to use the opportunity to show off your overflowing knowledge with a fresh one. Yeah. You'd feel a little bit lame if you just dusted off a homework assignment and changed the values.
Now, if it's probable using Excel, to be able to use Excel on all the problems?
I don't know. Yeah, I don't want to wade too deeply into conjecture. Certain problems lend themselves to others, and others don't. Right. Yeah. Yeah. It won't be a split exam like that. That's not my intention.
And we can use our own computer?
Yeah.
Okay.
Right. You can use the tablet if you dare, or bring in your own laptop. Yes? I don't know. Probably not. No. Yeah, you're going to get a big heaping dose of water gems on the project, so we really haven't spent any time in it this semester. Yeah. Any final questions?
An equation pack we'll get on Thursday?
Haven't I already given you guys the FE review manual?
FE manual?
Yeah, yeah. Did I give you another one this semester? Okay, I'll print those off and give you, because they've issued a revision. Version 9.1 was issued a couple of weeks ago, so I'll give that to you on Thursday, assuming you're... You can put anything you want on the self-written one. Remember that the FE has the format of some of those equations may look a little different than you're used to, which is why I give it to you now, so that you get acquainted with how it looks. All right, let's talk about pumps, but first we're going to look at some pictures of what's going on in Zimbabwe. Anybody heard about the dam failure in Zimbabwe? Did you? Did you see these pictures already? It is a geotechnical failure more than a hydraulics failure, so we can point the finger of blame at those guys, but it's still kind of interesting from a hydraulic perspective, the scale of the facility that's falling apart. It's been under construction, I think, since 1998, so they've been working on it a good long time. And that's right. Yeah, better now than later, I guess. And they've settled into some complacency.
You go back?
Yeah.
You can see that.
Yeah. I really don't understand what it is they're doing. Right, yeah. I mean, clearly the water seeping through part. This isn't where they're intending water to go, right? This is the main spillway here. And this must be some sort of a mistake spillway. Or Yeah. Zimbabwe is one of the most corrupt countries in the world, so it's not, I guess, a surprise that something like this would happen where inspectors are being bribed and probably materials that have been specified aren't being used. You know, nothing's the way it ought to be. You'd expect failure. So.
Professor Huffman said they built part of it poorly, and then they got another company to come in and look at it, and they were like, you should just tear it all down and redo it because this is bad.
Yeah.
No, so they just
Keep going.
Right. Yeah, that's a sort of the idea of sunk cost that you learn about in engineering economy, where you're so far into a project, it seems mentally you can't afford to quit. That, well, we've made it this far. We have to keep throwing money at the problem no matter what. It's like when you've put on new brakes on your car and maybe you fixed a broken window, and so then when something else comes due, more money, even though your instincts tell you, I should just walk away from this car. You can't do it because of the previous investments you've made. It's probably a similar thing here is, you know, whatever government minister approved the project didn't want to look like a failure for tearing it down, and so they just kept going. It was probably, almost certainly, just an issue of personal pride rather than engineering sense. Yeah. Okay, but pumps is what we're talking about today, far less dramatic than a failing dam. A pump adds energy to a system, and most of the pumps that we'll be dealing with this semester add energy to the system in the form of an increase in pressure. Remember that energy can exist in three forms in the hydraulic sense. The head is the pressure head, elevation head, and velocity head. And although a pump has the effect of speeding up flow through a pipe, that's not how it directly adds energy to the system. The pump, if you think about what comes into a pump and what goes out of a pump, here's our pump, and the water that comes in and the water that goes out is at the same velocity if the diameter of the inlet and the diameter of the outlet are the same. And so upstream and downstream, the water's at the same velocity. That tells us that the pump did not add energy by increasing the velocity head. And you can see that in this case, the pipe is horizontal, and so the elevation of the flow in and the flow out is the same, and so the pump didn't add Z. And so in the case of most pumps, it's adding pressure to the system so that downstream of the pump, the pressure is higher than immediately upstream of the pump. The exception to that is a positive displacement pump like this, a screw pump, where water is actually lifted from a lower elevation to a higher elevation by a rotating screw inside of a trough assembly or some sort of a jacket that retains the flow. And I've got a little recording here that shows a screw pump in action. Not sure of the history of the screw pump, but it's fun to watch the video. Let's see here. All right, so you get a sense that the water is just lifted, and each one of those revolutions brings a fixed volume of water and then discharges it. The efficiency of a pump like this depends on how watertight the seal is between the case and the rotating screw, because clearly water could seep down the edge. Also, the rotational speed of that pump is limited. If it increases too much, it's just going to be flinging water everywhere, and so it can't. It doesn't have an unlimited capacity for, increasing the rotational rate and increasing the flow rate of water that's being lifted. So it adds energy in the form of elevation. Now here are some neat little animations that show other types of pumps. And you can see in the case of a rope pump that what's happening is that a plug on a rope or a string is going through a cylindrical shaft, and the water gets stuck in between each one of those plugs. And then as it gets up to the discharge spout, the water just flows out into the bucket. Each one of these pumps are called positive displacement pumps because in each revolution or in each cycle of the pump, a fixed volume of water is delivered to the discharge. And so in the case of the peristaltic pump, and the peristaltic pumps are really common in environmental engineering applications in the lab setting, where you're trying to deliver a very exact low flow rate maybe if you're drawing water from a jar of acid to go into like a chemical concentration sampling device, like an ICP or something like that. There are these devices that tell you the concentration of pollutants, and you have to have an exact flow rate of water being delivered to the downstream end. And so the way to handle that is that with each revolution, the volume inside of that plastic pipe, the plastic tubing that's getting flexed, is delivered as a discharge. Each one of these have their own relative advantages, but mostly I showed you these because they're interesting to look at the animations. They're not common. Probably the peristaltic pump is the most common. Yeah. Oh yeah. Mm-hmm. They're none of these. They're this kind of pump. Yeah, they're a radial flow pump, and this is the far more common kind of pump. This is what you'd see commonly in all but the largest applications. And the way that centrifugal pump works is that inside of this is an impeller that has vanes that there's a variety of different shapes and number of blades and length of blades, and the design of these vanes varies based on the rotational speed that's going to be intended, because sometimes people use the phrase pump to mean both the pump and the motor. But it's important for our purposes to distinguish that those are actually two separate devices. The pump is coupled to a motor, but both the pump and the motor are going to have their own independent characteristics. Ordinarily, a motor will rotate at a fixed speed. And for very large motors, the only way that you can get it to go at a varying speed is to use something called a variable frequency drive, a VFD. And those are very expensive things that actually adjusts the frequency of the alternating current that goes to the motor. And so, you know, our electrical plugs here are at 60 hertz, meaning that the alternating current goes back and forth between positive and negative 60 times per second. To get a motor to spin at anything other than its typical standard rotational rate, you have to have a device that adjusts the frequency of electricity from 60 hertz to some other frequency. But that aside, the way that this works is the water comes in through the suction side, and ordinarily the tube that goes to the suction side is going to be larger than the discharge tube. And that's an important, and they do that for a very specific reason, that the suction side hose is usually larger than the discharge side hose, having to do with cavitation. But as the water enters the pump, it reaches the blades are rotating, and that accelerates the flow because of the radial flow that's there. There's a centripetal acceleration that accelerates the water out the pressure side. And so there can be cavitation inside of the pump. Remember, we've talked about cavitation before and how that is where the pressure of the liquid is lower than the vapor pressure. And the cavitation can cause a boiling, and the collapse of those little cavitation bubbles of vapor can send a shock wave through the fluid that causes damage of the pipe surface. Besides the centrifugal pump, the other pretty common pump is axial flow. And it's similar in that it's increasing the pressure of the water as it flows through the axial flow pump. But the difference is here that instead of changing direction, you know, in the case of this pump, the water goes in and then it exits at a 90-degree angle. In the case of the axial flow pump, the water doesn't necessarily have to change direction as it goes through the impellers. It generally will change direction because there's a shaft that is allowing the impeller to rotate, and the only way to make that happen is to have a motor on the other side of the shaft eventually, so you couldn't have the water flowing through the motor. So normally there will be a bend after the axial flow pump. But here the impellers just look a lot like a boat propeller would. And the same sort of concerns exist in an axial flow pump about the possibility of cavitation. And so the designer has to select the pumps keeping in mind that you have to avoid the case of negative pressures.
When you have a jet ski,
Yeah.
those pumps that are, I mean, I think it's Axial.
I don't know. It seems like a big pump because it's a jet of water that comes out, right? Yeah, it's probably something similar to this, but it's on the inside of the device rather than out. Okay, so this is showing both of the applications in real-world kind of use, where this might be a pool of water, or it could be meant to represent also the water table. You know, sometimes a pump like this would be used in a screen of a well, and the water would flow into the screened pipe shaft and then go up towards the discharge. But think about what happens pressure-wise. What is the pressure of the water right here at the surface in terms of gauge? 0. It's atmospheric pressure. And so the water pressure and the air pressure are the same at the surface, right there. Okay, so roughly speaking, the water increases as we go down, and then we go into the pipe. And so now as we go up through the pipe, the pressure is decreasing for 2 reasons. Okay, we're going up, and so the pressure is decreasing because of that, right? But also the pressure is decreasing because there's head loss. As you go through that pipe, there's head loss. Anytime you've got, you know, the Darcy-Weisbach equation tells us H sub F is FLV squared divided by D2G. So water is flowing through a pipe that has a diameter, it has a length, there's some velocity, there's a roughness involved. And so as the water flows through this pipe, energy is being lost, and it's being lost in the form of a reduction in pressure. So what happens if we have a really high velocity as water flows through that pipe? There's going to be more head loss, and pressure decreases more quickly. Why are we worried about pressure decreasing too much? Cavitation, because if the pressure inside the pipe goes lower than the vapor pressure of the liquid, then the liquid will begin to vaporize. It'll boil. It won't be hot, but still it'll go from the liquid phase to the vapor phase. And so the sorts of things that tend to promote cavitation would be a long suction side hose, a small diameter, or large velocities. So I told you that ordinarily the suction side hose of a pump will be a larger diameter than the discharge size. Why do you think they make a big diameter pipe going on the suction side of the pump? It lowers the velocity and it increases the diameter. Both of those things are good in terms of reducing the rate that we lose energy. And so that means it's less risk of having the pressure in the water go below the vapor pressure. Okay, so yeah, in both of these cases, the nice thing about this this bottom example is that the metal shaft could be really long. You could separate the motor and the impeller. And so here, it's actually going through the suction to pressure side even before you get above the water surface. And so there's probably not a lot of risk of cavitation here, if any, because the impeller is below the water surface. This is nice and safe. But in the case of that top example, the things that we'd be on the lookout for, wondering, is it going to cavitate, is the pump really high above the elevation of the water surface? Because a vertical distance is going to decrease the pressure even more as the water flows from the water surface towards the pump impeller. Long pipe, small diameter. Gil, did you have a question?
We use that bottom from the bottom line.
Do you?
Yeah, because the atmosphere, methane and stuff
Right.
in the mine, it keeps the motor and the electric part on the surface.
Yeah, you'd want to have the...
Some of those shafts, I've seen them over 300 feet long.
Really? Yeah. I know that in groundwater wells for drinking water production, they'll usually use that to avoid cavitation, but luckily they don't have to worry about explosions in the same way that miners probably do.
And why does this one not have the risk of cavitation?
Okay, so think about the water goes from low pressure to high pressure instantly. As soon as the water gets into the impeller, as soon as the water touches the impeller, it goes from low pressure to high pressure. And in the case of this lower example, the impeller is down here below the water surface. And so the pressure starts to go negative when we're above the water surface. And so if the impeller was up here, then the pressure would be going from 0, because we're at the water surface, the pressure is 0, and then it's decreasing the higher up you get. But since this impeller is below the water surface rather than above it, then there's no risk that the water...
Just increases it more.
That's right, yeah. There's never any place inside of the pipe that the pressure is going to go below 0 gauge.
The cavitation risk on this one is on the left side of the pump.
Exactly, yeah. The highest risk of cavitation here is just right before we get to those impeller blades, because that's when the pressure is the lowest. The lowest pressure in the system is right before the pump. Okay, there's a problem in your homework that talks about pump efficiency. And as I mentioned before, the pump and the motor are two separate devices. And so if you want to find the overall efficiency of the system, then you simply multiply the motor efficiency and the pump efficiency together. And they're usually expressed in terms of a decimal, 0.75 for the motor efficiency, 0.5 for the pump efficiency, or what have you. The power equation I've provided here, and in SI units you end up getting, if you multiply cubic meters per second, which is the Q, the gamma would be newtons per cubic meter, and the pump head would be in terms of meters, then what you'll get out of the power equation is watts. And so if you want kilowatts, of course, you divide by 1,000. In the British gravitational unit system, the Q is going to be cubic feet per second. The unit weight of water is going to be 62.4 pounds of force per cubic foot, and the pump head would be in terms of feet. And then you divide by 550 because there's 550 foot-pounds per second in a horsepower, and that would give you the power in terms of horsepower. Well, that's what the power equation looks like in the FE review manual. And that's why I put it on here is, it's just to illustrate that, I say P for the power equation, and that's what's in our book. But then on the FE exam, they say W dot, which I take it is probably a thermodynamics variable, the way of expressing it in thermo. Not having ever taken thermo, I can just only speculate. I'll let you guys figure that out, because you do take thermo, but I don't. All right. So the factors that affect pump efficiency include what type of fluid is being pumped. Different liquids have different performances as they're going through a pump. There's different risks of cavitation. With more volatile fluids like alcohols and organic constituents, there's more of a risk of cavitation because they're much more highly volatile. Their vapor pressure is greater than that of water. Efficiency is affected by the pipe diameter and the pump diameter. And ordinarily there will be series of pumps that have the same typical shape of the impeller, the same kind of characteristics. There would be a whole family, like there's a 6-inch version, an 8-inch version, a 10-inch version, and they have similar performance characteristics. So there are curves we can look at that describe what their performance looks like. The other thing is that a pump doesn't have the same efficiency when it's rotating at one speed as it does when it's rotating at another. A pump may be very highly efficient, maybe 85% efficient at 1200 RPM, but then if you take it down to 1000 RPM, it may not perform anywhere near that good. And so there's a very complex chart that describes how pumps behave at all range of these flow rate and flow characteristics. We'll take a look at one of those example charts that's put out usually by the manufacturer. The manufacturer does a lot of testing to specify how the pump behaves in a range of conditions, and their engineers whose whole job is just to select pipes for different applications. I remember seeing a pump engineer job posting when I was graduating. energy goes into the pump, and so we talk about efficiency. Efficiency is how much energy went into the pump versus how much goes into the water. And the balance, the amount of energy that doesn't go into the water, is lost mostly to heat. And the water heats up just barely. It's the increase in heat going through the pump one time is almost imperceptible. But if you pump water recirculating it over and over again, the water out of a reservoir and then just dump it back into the reservoir, you can see the temperature increase gradually over time. Yeah, the temperature of water in the reservoir will increase over time. Pumps have these performance curves that the manufacturer provides, and this is a very simplified version of what a performance curve for a pump may look like. And it has a couple of characteristics. First of all, there's something known as a shutoff head, and that shutoff head is the amount of energy against which the pump can't even deliver any flow rate at all. And so, for example, if I was trying to lift water, in this case, the shutoff head is 24.4 meters. So if I had this particular pump and I was trying to pump water 25 meters, it wouldn't be able to do anything. There'd be all the water in the pipe, and I'd turn it on, and the pump wouldn't be able to do a thing. It would maybe, the blades would just seize up, or they'd spin, but the amount of pressure it could generate wouldn't be enough to actually get the water to flow more than 24.4. Then you can see that if it's working against less than 24.4 meters of head, then I'm going to start to see some flow rate. And as the flow rate increases, the head that it can generate decreases. Or I guess the other way I should put it is, if it's working against less head, then it can move a higher flow rate. And that's the typical characteristic of a pump, is that as the head that it's working against goes down, its capacity for flow rate increases. So as the head is increasing, the flow rate from the pump decreases. And the curve is sometimes an actual image, and in the case of one of your homework problems, they provide a curve in graphical form rather than an equation. Here it's in both graphical and equation form, but in one of your homework problems, you have to sort of look at the curve and translate that into an equation like this, by plugging in a couple of points and finding what is the coefficient before that q squared. So on the one hand, we have a pump curve, and a pump curve says what the pump can do, how much of a cutoff head it can fight against, and what the flow rate's going to be under a variety of different head situations. On the other hand, we have what's called a system curve. And this is an illustration of water going from one reservoir to another. The Q and the arrow, that indicates it's being pumped from this lower reservoir to the higher one. You can see that there's a delta Z that's indicated, and so the water's having to lift up a certain amount. And then we know that there's a certain pipe length here. And so you can generate a system curve. Now this looks different from the pump curve that we just had. What this system curve is saying, in this case, the typical trend of it is there's some H sub P, the minimum amount of H sub P. What do you suppose that distance is? Let me draw it on the board here. Okay, so we're saying this is flow rate, and this is pump head. And pump head, of course, has units of meters. We know that pump head has units of meters. So what does this amount right there correspond to? Exactly. That's delta Z. Exactly right. So the water, how much energy do you need to move the water? Well, if you provide delta Z, if the pump's providing only delta Z head, then you're going to get zero flow rate. But if your pump is going to provide more than delta Z, then you can get a certain flow rate. Now, why is it that this curve is gradually getting steeper and steeper? What's the interpretation of that? Why isn't it and I'll say you'll never see it be a straight line. It will always be a line that's getting increasingly steep. Why is that? That may be related to it, but it's not the cause of why the curve is getting steeper. Think about just in terms of the system. Water's flowing through a pipe. Why is it that as the flow rate goes up, that we need more and more?
As flow rate goes up, velocity
Efficiency
goes
of
up
the
squared.
pump gets less.
Okay, this remember isn't about the pump. This is just the system curve. Now the pump also is tapering off in sort of the same range, but it turns out what Levi had said about the velocity is important. So go into more detail. What was it you meant by the velocity squared?
Flow rate velocity is just by itself, but then velocity squared.
Okay, so remember the pump is fighting against two things. It's lifting the water, so that's the delta Z part of it, and then everything above the delta Z is it's fighting against head loss, friction losses. Water flowing through the pipe is going to face resistance. The more you increase the flow rate, the more resistance there's going to be. And it's not a linear relationship. Head loss, H sub F, is FLQ squared divided by D2GA squared. And so that when the flow rate increases, the H sub F has if flow rate doubles, then the head loss increases by a factor of 4. And so it's a nonlinear response because of the friction losses. So why do we need the pump? It's because the system curve needs to overcome the delta Z and also the frictional losses. And so the way that you find out how is this combination of a certain pump in a certain situation, what's it going to actually do? What will be the flow rate that it does? Because we have a curve that says this is what the pump can do. The pump can do that. And this is what the system needs for a certain flow rate. And so the way that we find out what the actual flow rate is going to be is to put those two curves on top of each other. And by the way, we can create a system curve just by looking at the delta Z and then the flow rate that's going through the pipe times the pipe characteristics for friction losses and if there are local losses in the system. And so bends, inlet, outlet, those things are what contribute to the local losses in the second term of the system curve equation. Okay, so we've put the two curves on top of each other and you can see that there's an operating point. If we'd had a different pump, if we'd had a more powerful pump, then maybe our operating point would be at a larger flow rate. But we're right here at the intersection of those two curves, and so numerically speaking, what we do to solve for the flow rate is we set the two equations equal to each other. Remember that both of the equations are expressed in terms of an H sub P. Both the pump equation and the system equation have H sub P on the left side and then other variables on the right side. Now, we have the old dilemma that our system curve, remember, our system curve depends on F. F depends on flow rate. So flow rate depends on F. F depends on flow rate. So where do we start in finding out what the pump curve is going to look like unless we know what the friction value F is? And so we start these problems by assuming fully turbulent flow. And then in a second iteration, we can check to see if fully turbulent flow assumption is valid, and if not, use the guess flow rate to calculate an updated F value. So remember, the fully turbulent assumption is where we ignore the second term of that equation, and then the friction value only depends on the ratio of K sub S to D. So let's work an example here. We're given both a pump curve. So this is the pump curve that's given. And we know some information about the system. We know that there's a length of pipe of 120 meters, a diameter of pipe that water's flowing through, the roughness, the local loss K value, and the delta Z, the vertical elevation difference between point 1, which is the origin, and point 2, which is the destination. And so to find out what the flow rate is going to be, we simply are going to set those two equations equal to each other. Okay, so we have a pump curve. Our pump curve is H sub P is 24.4 minus 7.65 Q squared. And then we have to create the system curve. System curve. Okay, we are going to, first of all, need to find the area. And so the area is pi d squared divided by 4. The pipe cross-sectional area is 0.04909 square meters. We also need to know our guess F value using the fully turbulent flow assumption, 1.325 divided by the logarithm of 0.25 millimeters divided by 3.7 times 250 millimeters. And we'll square all of that. We get our guess fully turbulent flow assumption, F value of 0.0196. Assume fully turbulent flow. So then we can create the system curve. It's going to be that the pump head required is we have to add at least 9.1 meters, because that's the vertical elevation that has to be overcome. Plus, you need to add even more pump head if you want the water to flow. So we do want a positive flow rate. So we're going to say it depends on the flow rate, Q squared times F, which is 0.0196, times the length, which is 120 meters, divided by 2G times the area squared, 0.04909 meters squared, square that, times the diameter, 0.25 meters, plus we're going to factor in the local losses. So the sum of our K values, which maybe is valves or pipe bends, any kind of fittings here. So the sum of the K's is 2.4, and multiply that by the velocity head, which is 2 times G, 81 meters per second squared, times the area squared, 4909 meters squared, square that. And I said we're multiplying by the velocity head. Here's the rest of the velocity head over here, because remember, velocity head is Q squared divided by 2GA squared. So we're multiplying K, which is 2.4, by Q squared divided by 2GA squared. So all of that together, this part of it is 198.98. This part of it is 50.76. And the advantage of identifying a subtotal like I've just done here is, number one, it makes it easier for you to check your work when you go through the calculations a second time to verify that, yes, I got both of these subtotals. And the other interesting thing is just to compare the relative magnitude of the friction losses to the local losses. And here the friction losses are about 4 times the magnitude of the local losses. Any questions so far? So just to stand back and give an overview, the whole thing that we're doing right now, we're creating our system curve. And the system curve basically says how much pump head is needed for a certain flow rate. There's going to be 2 variables. There's going to be Q and H sub P. And so it's going to say how much H sub P is needed for a certain flow rate Q, based on all the characteristics we know of the system. And what we come up with for the system curve, H sub P is 9.1 plus 249.74 Q squared. And that is the system curve. So now our solution is to put the system curve and the pump curve equal to each other. Okay, so the pump curve equal to the system curve. And so the way that we do that is we say 24.4 minus 7.65 q squared is equal to 9.1 plus 249.74 q squared. We set the two equations equal to each other. That works out to be 257.39 q squared is equal to 15.3, or Q is 0.244 cubic meters per second. So this tells us what the flow rate's going to be when you pair that pump with that system. Now, the final thing we have to do to sort of tie up our loose ends is to check the fully turbulent flow assumption to make sure our F value doesn't need to be modified and go through the calculations again. And if we do that, we get a velocity of 4.97 meters per second by doing Q divided by A. We get a Reynolds number of 1.24 times 10 to the 6th. The K sub S to D ratio is 0.001. So we can go to a Moody diagram and look at how things match up. We've got a Moody diagram in here, I bet, somewhere. There's one. Wait. There we go. All right, so 1.24 times 10 to the 6th. That puts us here. And the K sub S to D of 0.001 in here. Okay, we're in the fully turbulent zone. So we're on the right side of that dashed line, just barely. So we're okay. We don't need to iterate the F value as long as we're on the right side of that dashed line, meaning fully turbulent. So if we were on the left side of that, then all we'd need to do is calculate a new F value based on the velocity that we just calculated. And then, went too far. All right, yeah, this is where we were, right?
So will the pump curve always have a negative side and system curve be positive?
Yes, it will. Good question. And the reason for that is that the pump curve is going to have the, let's see, the way that we could express the reason why the pump curve is going to be negative is that as the flow rate increases, the pump head that it can generate decreases because more of the energy is going to the moving water rather than an increase in pressure. And then the reason for the system curve going up is that as the flow rate goes up, so does the head loss. The head loss is going to be increasing as the flow rate increases. This is what a pump curve actually looks like. We were looking at a very simplified version of it. There's a lot of information on here, so let's take a look at some of the things that are shown on this pump curve. First of all, it's showing the head in terms of both feet and meters because the pumps are used both in the United States and internationally. You'll notice that it shows how much head can be generated at different rotational rates. And so if you pair a pump with a motor that does 3,600 RPMs versus 2,400 RPMs or anything else. The other thing that you find is that these curves are corresponding to the amount of, let's see, it's the efficiency. And so 50, 55, 60, those are efficiency curves. So this particular pump is most efficient for a flow rate of about 400 gallons per minute and against a head of 400 feet. So the way that you'd be picking, you know, if you had a book full of charts like this, first of all you'd say, you'd look at your system and find out, what's the head that you think is going to be required. And so you'd say, well, I need something that's going to add around 400 feet of head. And so you'd flip through the pump curves, and lots of the curves wouldn't even get as high as this. And then you'd compare pump curves to find out which is going to be the most efficient. And then the other thing that's on here is you can see something that says NPSH. And that has to do with the risk of cavitation that we're going to talk about in just a minute. NPSH stands for net positive suction head. And it's a way of characterizing how close you are to the point where the water is going to begin to cavitate.
You got a pump, I've seen it on job sites, the pump comes with a certain intake hose.
Mm-hmm.
I've seen people, if the intake goes longer,
Yeah.
have affect cavitation.
Definitely. Yeah, it increases the risk of it. Now, it's maybe not so risky if the pump is going to be at the same level as the water, but then if they put, you know, a pump on the top of the engineering building and they think that they're going to suck the water from, you know, a swimming pool at the bottom, that's not going to work, you know. So yeah, increasing the length that beyond what was given originally will increase the risk of cavitation.
The 50, 55, 60, those are the efficiencies.
Those are efficiencies, yeah.
So I guess this particular pump, the highest efficiency is reaching 65.
Yeah, maybe a bit better, because here's,
So you said, I'm sorry, 400, whatever.
yeah, what you do is you'd say at a head of 400 feet, then you can follow along in between these curves. So at 3,600 RPMs, it will do 300 gallons per minute and generate 425 feet of head, and then it would be 61.5% efficient. So you'd find out where on the efficiency curve after you look at the intersection of head being generated and capacity. Well, you can express the amount of energy that's required in terms of horsepower. So yeah, that's the motor you'd want to power it with. So you know, a pump that is moving this much water, you know, for the flow rate that's given, this is the amount of power that's going to be required to do that. Yeah. Okay, so what we're going to talk about now is this NPSH. Just as a reminder, this is a slide from fluid mechanics, and you can boil water either by heating it, and what heating the water does is increases the vapor pressure of the water, because vapor pressure is a function of temperature. But at normal room temperature conditions, water will have a vapor pressure of maybe only 17.5 millimeters of mercury. So ordinarily, water isn't going to just boil at room temperature unless the pressure, and this is an absolute pressure, by the way. The pressure that's indicated here is relative to vacuum. So if you go down from 0 gauge, or our atmospheric pressure is 760 millimeters of mercury. So if the pressure inside of the pipe goes lower than 17.5 millimeters of mercury, then boiling will occur. And cavitation is because of the negative pressure as the water goes from a reservoir and an elevated pipe. The higher you get away from the surface of that reservoir and the longer the suction side of the pipe is, the pressure gets lower and lower, and little air bubbles can form coming off of the impeller. We've talked about this in detail, but these collapsing vapor bubbles can cause little jets that have super high velocity and pressures that can pit over time the impeller and cause damage. Yeah, I think I've got a pretty good cavitation video, actually. Let's look here. This is high-speed photography, 63,000 frames per second of a propeller going through. It's tough to see, but it's a propeller rotating through water. It looks a little bit better on my screen than on yours. Let me put it on the other one. But you can see these little air bubbles here. They're not air bubbles, they're vapor bubbles, because it's the water vaporizing. Yeah. I guess interpreting it's probably just every bit as difficult, but you can see that those cavitation bubbles are actually visible as long as you've got a high-speed camera that can do 125,000 frames per second.
That picture right there, bubble streams are forming before they get to the
Well, this picture is a little bit deceptive because this is actually a propeller of a boat, but I'm using it as an illustration of that the water is flowing in here. The water is flowing as you're getting closer from left to right, and as you get closer to the pump, then the vapor bubbles can actually form. Now, they'll form along the blade itself because that's where the pressure is going to be lowest. Yeah, but it's to illustrate that the direction is from upstream towards downstream, and once you get past the impeller, there's no more bubbles because the pressure gets high again, and the vapor pressure is much lower than the water pressure, so the cavitation stops. No. This is some damage it can do. You can see that there's some erosion along the outer edge of the impeller here and along the leading edge as well. Okay, so NPSH, net positive suction head, is a way of measuring how much cavitation risk there is. And it starts off by you take atmospheric pressure. P naught stands for atmospheric pressure. Divide it by the unit weight of water. Subtract the elevation on the suction side of the pump. Subtract the head losses due to friction and local losses, and subtract the vapor pressure, and you'll find out this available net positive suction head, and it tells you how far the system is from cavitating. And you can also find a required NPSH, and that is what we got from a curve like this. These are NPSH required. So you can see that when the pump is doing 300 gallons per minute, then it's going to need about 11 feet of net positive suction head, so that you can calculate using this formula. You look at the system, and it's similar to here where we had a pump curve and a system curve and we set them equal to each other. In terms of cavitation, what you do is you look at the system and you calculate the net positive suction head available, because you're looking at how high of an elevation the water is being lifted and the head losses through the pipe and the vapor pressure of the liquid. And then you find out the pump characteristics and compare the two. And cavitation will occur if the required net positive suction head is greater than what's available. So if the available net positive suction head is too small, then those little vapor bubbles will begin to form inside of the pump, and the erosion will begin. Now, if they're equal to each other, that's what's called the point of incipient cavitation, meaning that the cavitation is just barely going to begin. So sometimes you'll see problems that say, what's the maximum elevation you could put the pump at? So you'd find the delta Z where NPSHR equals NPSHA. All right, let's just take a look at a quick example of cavitation. Okay, in this example we have a all right, we know the water temperature is 40 degrees Celsius, and so that gives us a certain vapor pressure. We can look up the unit weight of water based on the given temperature. We've got an elevation difference of 4.3 meters from the water surface to the pump, and there are losses on the suction side of 1.6 meters. So the first thing we're going to do is find out what is the NPSH available. And that's the pressure head minus the delta Z on the suction side minus the head losses minus the vapor pressure head. Okay, so 101,325 newtons per meter squared is our atmospheric pressure at sea level. 9732 newtons per cubic meter is the unit weight of water at 40 degrees Celsius. There's an elevation difference of 4.3 meters. The suction side head losses are 1.6 meters. And again, I have to emphasize that it's just the losses on the suction side that we calculate. We don't include the head losses after the pump. It's just before the pump that we're concerned with. So 1.6 meters, and then subtract the vapor pressure, 7,300 newtons per meter squared, divided by 9,732 newtons per cubic meter. Okay, so altogether that is 3.761 meters. And so here we've got NPSHA. What's available is 3.761 meters, and that's greater than NPSHR, the required 3.5 meters. So there will be no cavitation. They'd sometimes just tell you the temperature of the water, or if no information is given about the temperature of water, you just assume room temperature water, and so then you'd go look at the value for 20 degrees. Yeah, it's vapor pressure, yeah. So what would happen to make the system start to cavitate? What could we do that would make the system start to cavitate? All right. So this water surface, if this is a pretty small tank, this water surface is going to be going down, right? As the water surface of the origin tank decreases, that's going to increase the delta Z. And so all we need is for the water surface to go down 0.211 meters, and cavitation is going to start. So this is actually a pretty risky situation. Or if we increase the flow rate, that would be another thing that would increase cavitation, because if you increase the flow rate, then the head losses will be larger. So that would be another risk. Anything that makes these terms bigger. Increase the delta Z, increase the flow rate would have more head losses. Or if you have warm water, then it's more likely to cavitate than cold water, because warm water has a higher vapor pressure.
As the water level of the source reservoir lowers, you're also increasing the flow rate because of the pump performance, right?
No, actually, the flow rate would be going down because there's more of a delta Z. Yeah. Okay, I have provided a couple of tips for you to use on the homework assignment that's due next Tuesday. Some of you are probably not familiar with the term a metric ton. You've maybe heard of like other kinds of tons, but a metric ton is a, I was thinking of something different, but 1,000 kilograms is a cubic meter of water. Levi knows what I mean. To convert between a kilowatt and a horsepower is in the front book. The front of your inside cover has a lot of conversion factors. And the K sub S valued for copper does not appear in the textbook. And so the value you can use for the K sub S, meaning the equivalent sand roughness for copper, is 9.16. For problem 9.16 is shown there. I mentioned already that you're given actually an image for the pump curve, and you have to take that image and turn it into an equation to be able to solve problem 924. And so you have to find this C value, the prefix in front of the Q. And then finally, in problem 927, it asks you to take some info from problem 923, which isn't in your list of what you need to solve, and so just use these values so that you can solve that cavitation problem. I didn't want you to have to do both of them just to get these values, so you can use those ones directly. So actually, we've gone over the material, all the material that you need to know to solve that homework assignment. It's not due until a week from today, but if you want to check your answers before then, I'd be happy to go over it with you. All right, I will see you on Thursday.